Okay, so hi everyone. I'm Tyler. I'm 971, the 971 student software lead, and today I'm going to be talking about some of our software architecture and just how we do things on our team. So the goal is to show some of the aspects that go into how we get our robots from looking like this to this. So the 971 code base has been in development since around 2012, and since then it's gone through many different iterations. We've reworked many of the aspects of the code structure, bring it to the point where it is today. And so today I'm going to talk about some of those specific components that go into building a reliable and predictable robot, and how our software development practices work. And while this represents many years of programming, I think there's certain aspects that every team can benefit from, whether you're a veteran team trying to improve your code base or you're starting out from scratch this year. And one of the main themes you'll see is abstraction, and that makes sure that we can adapt our code base easily without having to rework everything when we want to make certain changes. So here's our general code stack layout. While this is greatly simplified, it shows some of the overall aspects that go into our coding layout. So I guess one of the primary aspects of any robot system is the control loops. And these are what actually take various inputs, such as goals and current robot status positions, and they convert them into outputs, such as voltages, that actually get run on the robot. Another aspect is Wpilib Interface. And this is a separate module on our robot, and what this does is it handles all of the communication with Wpilib. So rather than using Wpilib every time we want to, like for example, in our control loops, we have a separate process that handles all of that communication. It's dedicated just for that. Next, we have the joystick reader, and this is another distinct system. This communicates with Wpilib, and this is what actually sends the goals to the control system to tell it what to do. So if it reads in, say a move left on the joystick, then it'll send a goal to the control loop to move the robot left. And you'll notice between all of these systems we have these arrows pointing, and these represent our message passing system. So this allows us to send data between these different processes almost automatically. And then surrounding all of this, we have the logging system. And this ensures that we are recording all the data that happens on the robot, and it's useful for testing and debugging, for example, in the lab or after a match. So again, here we have a few different aspects I'm going to talk about today. So I'm going to talk about that messaging system, which is very crucial to how we lay out our code. We have Wpilib interface. We have the control loops. And testing infrastructure allows us to make sure the code will run with somewhat predictability on a laptop before we actually put it on the robot. And then finally, we have a logging and replay system. So this allows us to relog the data on the robot, and then we can replay it later to see what exactly happened. So first, I'm going to talk about this message bus system. And so what this does is it defines a standard data structure that's available to all processes that are running. So for example, we might have a sensor data structure, and this will contain all of the different sensor outputs that can be passed from Wpilib back to a control loop. So the overall goal of the message bus is that it's almost like a class in a programming language. However, it's designed to be passed between different systems almost automatically. And so it's kind of implemented as a broadcast, publish, and subscribe system. So the way this works is that, say we have Wpilib, and we want to send a sensor data to a control loop, for example. What it'll do is it'll generate a new message, and it will then package up all that data and make it available to everywhere else on the robot. And then any other system at a later time can go back and retrieve this data automatically. Or then let's say we have the control loops and they want to send a voltage back to Wpilib to write out to the motors. They'll generate a new message, publish that, and then finally output it. And so this provides a standard data access to all of our systems. So rather than having to go into access a class directly and pass data to it, we can just update this message and then it'll send all the data automatically. And one benefit is it provides an overview of all the properties of the robot at a glance. So rather than having to look into the class definition and figure out exactly what's going on, you can just look at this queue and assume, oh, if I update this queue, it's going to work, assuming the other systems are implemented correctly. So for example, with the joystick reader, you don't have to know anything about the control loops. You just know you have to make a new goal message with like the height of the elevator or the speed of the drivetrain, and it'll just work, assuming the control loop's already implemented. And there's typically 4 types of messages that are part of our control loop process. So we start with a position, and this is the data that almost the raw sensor values that are read by Wpilib Interface. And these are published to a position message. Then they are converted into a status message, and this represents more human-friendly values, such as the height of the elevator, for example. And then next, we also, from that, we combine that with our goal data, and the goal data is retrieved, usually generated by the joystick reader. And finally, within the control, to produce an output, which is just like voltage, or for example, if we want to actuate a solenoid, it's things like that. And this abstracts interaction with a subsystem. So we aren't going directly to the control loop and telling it we have a new goal. We're just publishing a new goal available, and then the control loop can go back and interact with that. And also, very important, the queues are available to all systems. It's a global state almost. And so even though these processes are all started separately, there's a single queue or single message that's available for all of them. And so here's an example message from the goal message from our robot this year. And so this is, if you're writing code to control, I think this is the goal message for all of the superstructure. You just have to look at this, and you just have to publish a new goal message for it. So for example, you can see we have an elevator, an intake, wrist, stilts, and then also rollers, which are just a single voltage. And also we have a suction, which is which of the 2 suction cups you want to apply suction on. And so when you're writing a joystick reader, for example, you just say, okay, create new goal, update the elevator with a certain height, update the intake with a certain height, and send, and you're done for that aspect. So that leads me into process separation. So this is the concept of having all these separate processes. Rather than running a single process on the robot that contains all of these different systems, they're all separated out into separate processes. So it provides better organization of our code, and it also helps us avoid some problems that can occur. And you'll notice, everything is a separate process. So these are all separate processes. They're running actually as separate processes on Linux. They're not separate threads. They're actually different applications almost that can be run independently, and they all communicate via this message system that's basically set up and configured by a core process, which I don't show here. But the way they communicate is with these messages, and these are implemented as a queue in shared memory. So that core process sets up a block of shared memory that all the other processes have access to automatically, and they can then publish to those queues, and then they can be read back by the other processes at a later time. And one of the benefits of this is that individual processes can crash or be, if we e-stop them or something, they can be all done independently without bringing down other parts of the robot. And while that usually doesn't happen, one of the other main benefits is that we can have different priorities on each of these different processes. So for example, we might want the control loop to run at a higher process than the logging system, because the logging system is taking all this data and is writing it out to disk, which can have significant latency. And so we want to make sure that the control loops, for example, are running at a higher priority, so that they're running consistently on every tick of the robot, while the logging can be deprioritized, since it's a longer operation. So now I'm going to talk about some of the specific processes in this system. So first, Wpilib Interface. And this is a single process that handles nearly all of our communication with the Wpilib libraries. And so as I said earlier, we don't have the calls to Wpilib in many parts of the robot. We have almost all of them concentrated in a single file that's created for each year's robot. And so this handles reading all the values from the sensors, making the calls to Wpilib, and creating those position and status messages. And then it also takes those output messages and writes those voltages out to the actual robot. And one of the benefits is it can be updated to for changes to Wpilib. Since Wpilib changes often, almost on a yearly basis, there could sometimes be breaking changes to previous versions. And so by using a Wpilib interface, we just have to update this single file, and now our existing code will run on a newer version of Wpilib without having to make any other changes. It also is one source of truth kind of for communication with the robot. So one problem that might occur, if you're making calls to Wpilib everywhere in your robot, you have no idea what the actual kind of final output is to the robot. So if it's, for example, the elevator is moving faster than you'd expect, you really don't know exactly where that's happening if you have lots of voltage calls everywhere. But by having a single location, we know there's only one time ever that the voltage could be updated, or only one time ever that the sensor position is read from. So it's consistent, and we know exactly what's going to happen each time. So now I'm going to talk a bit about kind of an introduction to control systems. Just briefly, like how it can benefit your robot. So I have a question for the audience. This is an example of an autonomous routine. So what we have here is where we have the drivetrain set to a voltage to go forward. We wait some time, and then we decrease the voltage on the right motor, and so we're turning left. And then we drive a bit forward, and then we drive straight, and then we raise an elevator and eventually release the section to drop a game piece. So does anyone have any ideas kind of what might not work 100% of the time with this example autonomous routine? Anyone? Yeah?
Setting the voltage will not necessarily create the same output from the motor.
Yeah, exactly. So if the battery is higher or lower, because batteries aren't always consistent, you're not going to get exactly 12 volts out of the motor every single time. Any other ideas along the same line? Yeah?
Also, when you're trying to drive straight and raise the elevator, you're only driving the right motor, not the left.
Well, we still have the left motor set to high here, okay. So I think that's maintained across the entire time. But yeah, so there are lots of different variations that aren't accounted for. So what if you're driving off level 2, right? What if the platform is more or less slick on the actual competition field, right? Will the motor skid and then not actually jump off at the same time? Or what if the battery on the robot is old, right? You could be running a newer or older robot battery on your robot in a match. And what if your motors are wearing out, or just the system in general? Right? What if there's more friction that's occurring, as the robot wears down? Or what if it's not precisely aligned on the field, right? You can try to set up the robot exactly how you want to, but it's not going to be set up exactly the same every single time. And so that could account for variations that may not make this work 100% of the time. So this brings us into the control loop section of our robot and how this can help produce a more reliable and predictable robot system. So here's the Wikipedia definition of a control loop. However, really what it's doing is it's just handling the adjusting a robot or any system from a current status to a goal status. Right? So we know all the information about what it's at currently, and we want to bring it to some target. And so it responds to real-world inputs much better. So for example, rather than using time, a control loop system might respond to sensor readings, such as encoders or potentiometers, or even like a limelight, for example. So some of the ways this is used on a robot, moving an elevator from one height to another. If you have collision avoidance between two different systems, so for example, if you have, this year we had an arm and an intake, and it was possible they could be in a position to collide with each other. And so the control loops would ensure that this was unlikely to happen, or virtually never. It could also be used for driving in a fixed distance, such as in that sample autonomous routine, where we want to drive, if we're having an autonomous routine, we want to make sure it's driving the same distance every single time, or almost every single time. And so with a control loop, you can make that much more predictable. It could also be, even just if you have a system to control a solenoid on your robot, right? That's a form of a control loop. And so it ensures consistent robot behavior in varying conditions. So the field you practice on with your team is going to be different than the actual competition field. There's going to be changes throughout the day, as if you're using an older battery, maybe you didn't have enough time to recharge. So there's lots of different things that are entirely unpredictable. A control loop helps to minimize that unpredictability. So response seems truth outputs. Also, once you program an existing control loop, you can almost use it kind of plug and play. So this year we kind of wrote a control system that can control many different systems on our robot just by configuring different input parameters. So we had like the elevator and the elevator and the stilt are, if you think about it, they're very similar. So right, so we tuned those parameters, and once we wrote that control system, we could use it for any different. We could send goals to it without having to make other modifications, right? So as I showed in the joystick, with the joystick reader class, when it's producing that goal, we just have to update that goal, and we don't have to know anything about the control system once you write it predictably. So here's a simple example of what a control loop could like, just to give you an idea. Now, I wouldn't recommend using this one on an actual robot, but I think it demonstrates what a control loop might provide. So here we have an example drivetrain class, and we have a set distance goal. So this lets you tell the robot how far you want it to move. We have a goal reached, and this tells us have we reached that goal, or almost approximately within 0.01 centimeter. And then we also have an iterate method. And what this does is it tells it would produce a voltage output, so to tell us how much the robot, what direction the motor should turn in order to move in the direction. So again, this isn't a great control loop, but you can see how when we implement it in our autonomous routine, it makes the autonomous routine much simpler. So we can do a set distance goal here for 2 meters, and then rather than having to wait a fixed amount of time, we just have to wait until the goal has been reached. And in the meantime, we iterate it to determine what the voltage output should be on the next time step. So this might be, a hundredth of a second, for example. Then if we want to, I didn't show this one in the class, but we could implement a method that has you could set a turn goal, right? And then you would wait till the robot's turned. And then you could also do the same with an elevator again. You could set a height, and then you can just wait until that height's been reached with a goal reached method. So I don't know why that slides. Oh yeah. So now I'm going to talk about how does this all come together on our robot for 2019. So we have all these different systems. I'm going to give some examples of code of how these things are implemented to show how much all this abstraction can greatly simplify the process of designing robot code for a given year. So first what we have here is this is a snippet of code from the Wpilib interface. And so what this is doing here is this is actually reading in that position message from the sensors, and it's producing that position message to send to the control loops. And so what we have here is we're creating a new message. We're copying in the actual value of that message from the sensors into that position message, and then we're just sending that to make that available globally everywhere. And run iteration is we can assume that's called automatically every iteration of the robot. Next we have here is a sample from joystick reader. And so what we have here is we have a constant with a position defined. So that would set the position for the elevator at 0.75 meters and the wrist to be facing forward. And then we have another method here called handle teleop, and we can assume that's called every iteration as well. And so what this is doing is it's giving us a class with all of the data of the joystick reader, driver station data. And then what we do here is we just create a new goal with superstructure goal, make message. And then we can go and check that data to see what buttons actually pressed. So we can see, so for example, if the K-rocket forward middle button is pressed, then we just have to update that goal, or we update a temporary variable with this elevator wrist position value. And then finally at the bottom, we actually update the message with that value. And then finally we send that. And now the superstructure can go back and read that value to determine what to do. So here's the superstructure code. And again, run iteration is called every iteration. And that's automatically passed with the unsafe goal. And so that's the position that's read directly from the joystick reader without any modification. So it may not be a safe place that the robot could move to, right? So we couldn't move the elevator to, that could have like a negative height for the elevator, which obviously wouldn't be possible. And then we also have the position, that value from Wpilib. We have an output, and that's, we're going right to that output message with the actual voltage we want to send. And then we also have the status message, which are those more kind of human-friendly values of position. And so first what we do is we update our collision avoidance goal. And so we have a separate class called collision avoidance. And this handles all of that collision avoidance between the different systems. And so we pass it the current status and then also that unsafe goal. And what that will do is it'll look at, we pass it not just elevator, but also the intake and all the other systems. And it'll look at all of those and determine what a safe goal should be for those systems. And so that code, is, for example, like let's say one thing that the robot did was if we had the wrist couldn't move past the elevator to the opposite side. It had to go up and over the elevator. So let's say we had a goal that had the elevator, the wrist moving from the front side of the robot to the back side of the robot. What collision avoidance code would do is it would say, okay, it would update, let's say the elevator was down and the wrist was facing forward. It would say, okay, don't move the wrist at all, but set the elevator, modify the elevator goal to be at a higher position. And then in a future iteration, when it detected that the elevator was actually at that higher position, then it would allow the wrist goal to go through while it held it at that higher position. And then finally, when it reached the other side, it would relax the elevator minimum and then allow that to drop back down. So then we can see here, we're setting the elevator position. So the elevator is an instance of a kind of a generic class that provides a control loop for for an angular or a linear system. So all we're doing is giving it a minimum position that we retrieve from the collision avoidance class. And then finally, we call this iterate method, and that actually runs the control loop for the elevator. And so we give it the goal, we give it the position, and then finally it reference to the pointer to the output that it's going to write back to. And then we can see here in the backend Wpilib interface, we're getting past an output message. And so this is the same output message that the control loop code, superstructure code generated in the previous iteration. And so now all we're doing is we're actually setting that speed on the robot output. So you can see how if you're building any one of these systems, you don't really have to know about the others. You don't really have to know about the others or any of their implementation. You can kind of just focus on that one system you're writing. So if you're writing the Wpilib interface, you just have to worry about getting that output out to the robot. Or if you're writing the superstructure, you just have to make sure you're taking in that current position and producing an output. You don't have to know how that output's actually getting out to the robot. So all of these different aspects help bring us to the testing infrastructure. And this is how we make sure that our robots are working on a laptop. We can test a lot of the systems before we actually put it on a robot, right? Because you don't want to run the code on the robot for the first time. Now you can minimize some things like we do still by, for example, running it at a low voltage, right? So it's not going to do anything wildly unpredictable. But it's still a lot safer to be able to test it in a controlled scenario before you're actually running this on your real robot, which you probably may only have one of. And so we design a lot of our testing code using this Google test infrastructure. And this is a C++ library that provides a lot of different tools just for automating various types of tests. So it's not FRC specific or anything, but it can do things like it can create the tests, it can set up all the test systems, and then also do things like checking greater than, less than, things like that. Or it can also do kind of templated tests. So let's say we want to test an elevator system with different combinations of input sensors, for example, an encoder or a potentiometer. Google Test can help automate testing those different configurations of that elevator class. And we also have a continuous testing infrastructure. So we have a server in the cloud that's running all of these tests automatically when you push your code. And so rather than, while you test on your laptop, you may not catch all of the tests since if you're not building the entire code base. And so by running it running a continuous testing system, we can ensure that none of the tests are broken before your code actually gets merged into the master code base. And we follow the test-driven development principle, which you may maybe go into that talk later today. And the basic idea of this is that rather than writing code and then writing your, for example, your superstructure code, and then writing tests that satisfy that code or match what the code's doing, you write tests that define what the expected behavior of the robot should be, and then you write code to satisfy those tests. And so the benefit of this is that you're not biasing your tests with what you expect the code to do. So let's say that if the superstructure code isn't behaving, you might be tempted to write a test that just makes sure that it passes without really knowing why that test isn't doing exactly what you want. But if you write the tests first before you start writing your code, then you can ensure that your code is matching what that test should be, and you're writing the code to match the expected behavior rather than writing the test to match what the code is doing, which may not be correct. And so we have both unit tests and kind of implementation tests. And so we have tests, for example, for like generic control loops, zeroing systems, the message system itself, AOS, which is kind of just a general purpose library of different tools we use. And then we also have tests for your specific code. So for example, the elevator on this robot gets tested, or the intake gets tested individually. And then we also have tests for like the collision avoidance system. So what we might do is we might pass it an impossible goal to go to, and then we can run it and see what will it actually try to do, right? Will it allow those two systems to collide with each other, or will the collision avoidance code make sure that they never are intersecting? And so the way this testing system works is we have a lot of, as I mentioned earlier, we have a lot of abstraction. So what we can do here is we can, for example, replace Wpilib with a sensor simulation. So this will take the voltage output and it will produce sample sensor reads back, and it'll add some noise and stuff to produce something that's plausible or pretty close to what Wpilib would return back if it were running on an actual robot. And then we can also, rather than using joystick reader, we can just use sample test inputs. So we can just tell it we want to go to this goal, rather than actually having an actual joystick to read from. And so this allows us to do testing on a laptop or on the server without having any physical robot to use. So if you notice here, we've removed everything that's specific to the RoboRio. Right? We removed all the calls to Wpilib, and we removed the joystick reader since we obviously don't have a driver station connected. And so we're just using this test setup. And one of the ways this is possible is because of that abstraction. So if you had calls to Wpilib in your control loop class, for example, it might be difficult to remove those out to do testing later. But by having this message system where we're passing data back and forth, we can just have something else create those messages other than Wpilib. So we don't have to worry about going into the control loop. We just have a test sensor simulation create those sample sensor values. So again, we use messages for all of this, and yeah, the control loops can be created to run with a sample plant system rather than a real robot. And one of the other things we use very heavily are C++ templates, and so this allows us to swap out different classes with each other. So for example, if we have a control loop, we might want to have different sensor combinations that we can tell it to use, for example, for the zeroing. So we might tell it to use an encoder and a potentiometer, or just an encoder. Or what we can do is, for testing, we can tell it to use a sample potentiometer or a fake potentiometer. And so by creating all these classes that can be instantiated with different templates, we can ensure that, well, we can make the code adaptable to different use cases. Or if we have, like, say, some new sensor combination, we could plug that in there instead. And then we also have logging of all of these messages. So if you may have noticed, surrounding everything, we have this logging system. And what that does is it records every bit of data that's passed between all of these systems automatically. So how does the logging work? Well, the logging, we record all of the messages that are passed between the different queues at around 200 hertz, which is the speed that all our control loops are running at. And so it's recording every bit of data that's passed back and forth automatically, since they're all sent using this message system. And then for testing, again, we can swap out these values and replace them with real ones. And what we can also do is, after we run a test, we can go back, and since we're logging everything, we can go back and read these logs to figure out why something happened the way it did. So we know what, we can see in the log what the actual goal was before we sent it out to the robot, or sent it out to the sample robot. Or we can see what the sample sensor reads back were from the fake sensor. And then we can also plot a lot of this data. So for example, let's say we want to test just the control system itself to see, for example, let's say we're moving an elevator from one height to another. We'll make sure that's moving smoothly there, which might involve setting the ramping up the voltage a bit slowly, and then toward the end slowing down the voltage or decreasing the voltage so we don't overshoot the target. And so we can run those tests to see how those systems behave. And then also, whenever the robot's running, basically, it's recording data from these messages onto a flash drive. So that's both before and during a match. And so this allows us to, after a match, if something didn't work the way we expected it to, what we can do is we can go back and plug that flash drive into a laptop, or just read it directly on from the RoboRio. And then we can go back and see, why did something happen the way it did, right? What did the robot receive that it made it do something that we didn't expect it to? And also part of the logging system is we have what's called a log streamer. And so this allows us to view those logs live while the robot's running. So it may be difficult to debug a system that's running on the robot if you don't have you may be doing you could do printfs or something, but that doesn't capture all of the data. So with the logging system, we can run a log streamer code, and what this will do is it'll read all of those global messages, and it'll display them on a laptop so you can view exactly what all those values are in real time while the robot's on, even if it's not enabled. And so, for example, if let's say a sensor is not working and we're trying to debug it in the pit, what we can do is we can hook up a laptop and run the log streamer, and then we can kind of watch that value on the screen and figure out, as we're adjusting the physical robot, what makes it fix whatever problem it's having. And then again, also this log data can be analyzed later. So let's say the robot did something, in a match, and we really don't know why it did that. So for example, if we were testing our vision system, right, and sometimes it didn't work exactly as we predicted. And so what we could do is we could take these logs and we could run them on a kind of like a replay system, and at the same time we could watch the match video to see what the robot actually did. So we could watch the video, and then when we notice the robot do something unusual, we could go find that same time in the logs and figure out why it did that. So then hopefully be able to correct that behavior for the next time. And so I think that's all I have for today. But I assume a lot of you probably have a lot of questions, and so I'm leaving the rest of the time open for questions about any of these systems if anyone has anything they're curious about or any clarifications. Anyone? Yeah?
Can you explain how you implement the process separation on the RoboRio?
Yeah. So all of the different basically each of our systems. So for example, the control loop or the superstructure, the joystick reader, those are actually separate C++ executables, and so those each have their own main method, for example. And the way that works is we write a superstructure main class or main program, and then what that does is it instantiates AOS, which gets it set up with to plug into that message system, and then it starts running the control loop, and then when something tells it to stop, then it stops and closes out. And so that kind of.
How does that interact with the field communication in Wpilib? That's just started a separate process and that runs the way it would on a standard robot?
Yeah. So Wpilib is basically what you'd see on almost every other robot, and so that's actually getting those values from the driver station when the robot's supposed to be enabled and disabled, things like that. So that communication you see on a more traditional code base, that's all being done in Wpilib. Yeah.
How do you test the logging?
I mean, I guess, yeah. Oh, so the question is how do you test the logger? And I guess you can run the logger to see what it does with sample inputs. And I mean I don't. I guess we have unit tests that handle all of the different tests of each of these things. So for example, we can test the control loops, or we can test the zeroing, or we can test the logging system. And so we just have unit tests that run each of these things. And those are tests that are kind of separated, so they test just that one system in isolation while minimizing any other variables. And so we can make sure that that system works independently before we put it together with other systems and integration tests. Yeah?
In what format do you save your logging data?
The logging data, it's really just a stream out of all the data, but it looks kind of like a JSON format. And so it's basically just a serialized version of all of the messages. But then we can also do more fancy things with it, such as plotting it to make like a graphical view, or viewing it in a web page, for example.
We're looking this year at converting that over to either protobufs or flatbufs, so a more open source data format.
Anyone else? Yeah?
Do you have like a supervisor functionality that is used to monitor things, control processes?
Yeah, well, we have what I mentioned is called the core process. So I guess we have two processes. We have the core and the starter, and those get everything set up and configured. So those are, like, for example, creating that temporary file system with the shared memory for those messages, and then we also have a process which actually calls all of those executables to actually start them and get them running. Or if they crash, then it can restart them automatically. Yeah.
So the queues are going to use flat buffers?
Yeah. So let me talk a bit more about the actual implementation of the message system. So if you look at our code base, you'll see they're called queues, not messages, which might be a bit confusing. But the way they're implemented is like a queue system. So the way that works is there's a block of shared memory that's allocated, and then when a process wants to update that queue with its current with a new value, what it can do is it creates a new message, and then it grabs a mutex on that queue, and it pushes its new data into that queue, and then it increments a counter so that another process reading that data knows which place in the queue to look. And the queues only store a limited number of messages, and so when you grab the current value from a queue, you only have basically a certain amount of time to use it before it's overridden. But usually you assume that hopefully that system's running, that iteration's running fast enough that it'll be long done with the queue value before it's overridden again. Thanks everyone for coming today. I hope you learned something, and thank you.
Hi, I'm Ethan Stone. I'm a student on Team 971. We hope you enjoyed this video. For more videos and resources, please subscribe and visit our website at frc971.org.